from the source to its destination. We have the routing algorithm with the least cost path, and that's the deep starting algorithm 1, which I think most of you found it very easy to do. Most of the question was how many nodes last year? Last year 16 maybe. But this year I'm not sure. If it's that, I usually try to skip it, but no. So what we're going to do today is mainly focusing on addressing within the network layer. And I'm going to remind you what's addressing within the data link layer. MAC addressing, exactly. So MAC addressing mainly are your data link layer addressing, where we mainly focus on MAC addresses rather than focusing on anything else. So therefore, MAC addresses are what? Everyone remind me? Yeah, well, that's an acronym, but what's the MAC address itself? What is it? So it's a 48 hexadecimal bit that refers to a physical address within your device, whether that's a mobile, whether that's a laptop, a PC, whatever that is. So mainly it's referring to your permanent physical address within your device, whatever that device is, or let's call it host. So therefore, we're going to see what are the differences mainly between IP addressing, i.e. network layer addressing, within MAC layer addressing. Do you need both of them? Do you need one of them only? We are going to focus as well on something called ARP, Address Resolution Protocol, the association between those IP addressing and MAC addressing. So let's go to MAC layer addressing is not routable. Why is it not routable? First of all, MAC addressing are flat and permanent. So what does that mean? So if I want to refer to a MAC address within a local area network, is there any identification or any referencing referring to that 48 hexadecimal bits that is referred to somewhere in the network? Yes. How is that? No, there isn't. And if I would write now a MAC address, just open your mobile device, go to setting, and now go to your physical address. You just see a 48-bit hexadecimal part written in this way. A1, F0, 1, 2, and so on, 48 hexadecimal. There is no identification or referencing to anything that this, for example, belongs here. So let's say this is your topology, trying to connect through a router. So how is this, let's say this belongs to this machine, machine A. So how does this MAC address identify we are belonging to this section of the network, not this section? There's no identification. There's no even a hint that this MAC address is referring to as a side, left or right, or anywhere within your local area network. So imagine if you have a one rather than an actual local area network. I'm dealing with continents of connections. There's nothing. If I purely depend on your MAC addressing, that'll be a nightmare. Even if I have that table, and you remember the table where we forward, it's not routable. It's just forwarding within one switch. What was the routing mean? That means that if I have a routing algorithm, I need to go through the full trip, i.e. going past all my routers to reach my destinations. MAC cannot do that. And even if we try to use it, some cases we said, yeah, we'll use broadcasting. What would that affect if I heavily depend on broadcasting? That will create a delay and overhead and create so many issues within if I depend heavily on MAC addressing and broadcasting. So part of the today focus is we are saying that there's no relation between a host MAC address or a subnet. Although a subnet here, the keyword of subnet is not being defined, a subnet is referring to a section of a network, a local area part of the network, where you have multiple hosts connected to as a router or a switch. We call that a subnet. And that will be related with within your IP addresses in full details. So I'll leave that subnet definition in the later on of the lecture. But MAC, the main thing I want to show is MAC address cannot provide details of where that host is located within your network. Simple as that. MAC delivery relies mainly on broadcasting. With global broadcasting, is really impactful. It's really a nightmare. You will cause delay. You will cause an overhead. Depending on that table, that will be a large amount of numbers of broadcasting. So what I'm saying is, when I used to have broadcasting, simply I was dealing with just that section of the network. And even if I do broadcasting, that's not a big deal. You remember when we said we defined the virtual LAN, and for us to do that broadcasting within an isolation of traffic, we are speaking of one LAN. We're speaking of one local area network. If this has been expanded to this section as well, which is a different subnet, This broadcasting is a nightmare. Add to that if there is another switch in the middle and another switch. So that means this needs to be broadcasted towards every user within your network. And that's just a waste of bandwidth. Okay? So we need to find some sort of another type of addressing to sort that question and the issue within how to sort towards an addressing. So routing requires mainly a hierarchical, logical address, which provides one, a globally unique identification of hosts. Second, that's dynamically mapped to a physical address. So what I'm referring to today. What's that? That's your IP address. That's mainly your IP address. And I'll explain exactly what is an IP address, what's an IP version 4 mainly, and then towards IP version 6. So delivery to the correct subnet requires a network address with these characteristics. And you just said it's an IP address. What's needed? Network layer addressing, you need both MAC address and network layer addresses. Why is that? Can you tell me? So IP addresses are used to route across a set of interconnected networks. What does that mean? We said that number of switches creates a topology within your network. So the word routing here, if I'm trying to send from A to B, that's routing. Going through each of your routing along the line to reach your destination. So that's routing. We said, okay, so routing here means I need an IP address to use that to route across the interconnected network. To get the packets to the right network, just focus, right network. Where is the host in this equation? So you might be having a network with different hosts connected to it. How can I know exactly which IP address belongs to which host? What do I need? Now, so I've used the IP address to reach the right network. Now I need to reach the right host. What do I need? You need a MAC address. So, okay, so now, wait a minute. You just said MAC address cannot be used within a full range of network. Okay, yes, I said, but if I reach the right network, therefore I need to know the host using the MAC address. So in other words, I need the both of them to deliver that packet to the right destination. IP addresses are used simple as your mail addressing, where you have the full details of your postcode reaching towards the number of the streets. Then you need the number of house. Consider that as your MAC address. Again, it's not the right relationship between those two examples, but at least it just creates the idea of a MAC is like the host exactly where does it sit with the IP address. Okay? Is that clear? Principle-wise. Again, I'll show the real connection and how is it exactly working. But the principle as it's done. How is it clear? Good. So MAC addresses decides what host should receive a frame. You need both the source and destination of addresses. Why do I need a source and destination then? Of the MAC address. Sorry? So I know? No. What do I need a source and destination? Remember when I was creating the MAC table? What did I always used to do when I used to have the source and destination? To do what?
Find the source.
No. Routing using IP addressing. Why do I need the source and address and destination of the MAC address? I'm reaching the host. Why do I need both of them? Simply to create, yeah.
Create the forwarding table.
It's creating the forwarding table, which is what do you call it? The smart, what was it? Self-learning procedure of creating a table of a MAC address. You remember that self-learning? We needed the source and the destination to relate the source to an interface. The interface is important. How many interfaces do hosts have? Your machine at the moment, you're using this Mac. How many interfaces does that Mac have? Why? How many places do you connect to the internet? Yeah, but all of those are, if you have a physical address, how many physical addresses do you have? Just one. Yes, you'll have a wireless one in Mac, but mainly that's one address to reach your outside environment. So if I want to connect now through the internet, and I'm operating wireless and wired, does that mean there's two connections to the internet or one? It's just one. Even if you are both operating, you'll just have the one with the higher speed by default. So if you tell it as a policy-wise, just use the wireless, you just use the wireless. So in other words, if you are a host here, sitting in the network, you'll just have one interface to connect to the internet. Simple as that. Same question to the router. How many interfaces the router has? Why? Again, I explained this in full details, but I need to just to show you exactly what I mean by interface and why is it important. So let's say this is a router. How many interfaces? Let's say there's a connection this side and this side. How many interfaces? It's 2. Why? Tell me, why is it 2 interfaces? What each one of them do? We said the host need 1 to connect to the internet. Why do you need 2 within the host?
Taking in and then using it on.
Exactly. So in other words, you have this side taking in and sending out the messages. So these are 2 different places, in other words. So this is a subnet, and that's another subnet. So you needed 2 places to connect. Even if you have a third connection, that means you need a third interface. A router is actually connecting more than one side, more than one subnet, creating a bigger local area network, not just a one-side small area network. That's why you need 3 sides of them, not 1, not 2, 3. So therefore, a host have 1 interface. Meanwhile, your router depends how many connections you have to the internet or to the other hosts. Therefore, how many interfaces you have. Again, that will be clearly identified in the next slides. When we deliver a message to a host, we still have to consider host to deliver the correct process in the host, and that means that's a transport layer. Mainly, when I'm trying to deliver a message within a higher processes, we need to deal with the transport layer, and that will come whenever we go to the transport layer rather than the network layers. Okay? Any questions at the moment? Why are those 2 important? Your MAC address, your IP address. It should make sense now. Why do I need both of them? So, let's have more explanation about your IP addressing and some sort of an IP address within a different sort of protocols. We have a protocol called X121. That belongs to a protocol suite of X25, and that's mainly what I'm dealing with is virtual circuit switching, where I need like a telephone circuit switching. So what do you need in telephone circuit switching? Mainly you need a zone, a country code, a public data network, then a number to reach the destination, which is like 0044, like they have within the UK. Within a landline, you need a zone as well. You need to have 0116 within that belongs to where, for example, Leicester. So again, depends on where exactly you get through. That's your code. Within your IP addressing, it's very simple. The IP addressing, as we said, is mainly a dotted decimal. We refer to it as a 4-byte dotted decimal number. So if I would have an IP address, mainly IP address would look like this. That's the version 4 one. Mainly it's a 4-byte connection. So therefore it looks like, I'll give a number. Again, it's a 4-byte, so that's divided by the dotted decimal. So there might be 192.168.0.1, for example. These are classified by network and hosts. So you have an identification, for example, this might belong to a network, you're referring where this network resides, and this might belong to the hosts, or how many hosts you have connected to it. There is a classification defining which byte of those are the network and which byte of those is the host. Okay? But the idea of having a network side is like delivering the actual address, similar to the code zone. It's trying to show exactly where this resides in the network. How many classifications do I have? I'll just explain that in the next slide. IP addressing mainly have 3 main classifications. First of all, the numbers that range of an IP address mainly goes from 0 to 255, the number of an IP range. Okay? This number can be referred hexadecimal, binary, that's fine. But usually we know them in a decimal format. In that way. They come in different range, they have different meanings, and they are defined as a global and an internal IP address. Sorry. So let's see what our classification that we have. We have 3 types of classifications. We call them class A, B, and C. And these are apparent classes, if I'm not using any sort of masking. Okay? So class A is mainly a part of a network. Therefore, if I have a class A means the first byte is only a network component. For example, 10, 0, 0, 0. mainly that part, whenever the range of the nodes goes from 0 to 10, that's your network component. Meanwhile, those are hosts. That's your class A. Okay? So what I'm saying here, I'm saying that we have about that amount of bytes as network, and these are all host addresses. So how many addresses do I have as a host? Which one is higher? The host is much higher, so that's 8 bits plus 8 bits plus 8 bits. That's 24 bits of actual addresses. And when I say 24 of bits, I'm dealing with binary. Meanwhile, that's the only part which is a network. That's class A. So there is about around 16 million addresses of hosts. Some of them are, again, reserved, some of them used for multicasting, and some of them are addressed for an actual host. And these are the network side of the actual IP address. What about class B? Class B is just very simple. Rather than having the first part only as a network, now we have two parts of the network. So therefore, you'll end up having, rather than having a network and 3 types of hosts, you'll have a network side, and then 2 types of hosts. So the numbers now is being less. So that means there are 2 to the power of 16 as host and 2 to the power 14 as a network. I'll define why it's 14 and 16 later on. So now it's shared between the host and the network. I'm creating more addresses by reducing the number of networks. So when I increase the network, I'm reducing the number of hosts. And final class is the class C, which is a 3 part of the network of the IP address is a network components, and the final one is only host, where we use it within a small range of connections, small area networks, where you have a small number of users, because the numbers now is just 2 to the power 7 of hosts. These data classes, again, you don't need to be worried exactly what are these to the power what and how many numbers, but just identifying that there are a permanent number of users, i.e. with a host within the class of the network. So in other words, these number of hosts cannot be increased unless I provide some sort of masking. And that will be in your class-sensitive domain whenever we reach that stage. So each interface has a unique 4-byte addresses, and that, again, that's your IP address. Typically specified using dotted decimal notation. That's your dotted decimal notation. 110, 1, 2, 13. That's your dotted decimal notation. You're just referring to a decimal format. Okay? 3 different formats, assuming that 3 different network sizes. Class A is the backbone of the providers with many network devices. So whenever you have a big company that requires so many numbers of devices connected to this IP addressing, you need to have that class. Simple as that. Second class is an academical, typical military internet sites, where you have a range of from 30 to 60,000 devices connected to it. And finally, small user networks, class C, which mainly all your houses are. If you go to the main addresses, you'll find it 192.168, which is the final class, which ranges from 110 to 227. That's your IP address. That's very simple in a sense. These are just numbers, and I'm just saying these numbers belong to a class. How do I know the classes? The range of the numbers. From 0 to 10, to 10 to 100 and 110, these are your defined class numbers. But again, you don't need to worry about that. You'll not be challenged about what exactly this class this address belongs to which class. The main part of your networking is how to subnet using class-sensitive domain whenever we reach that. But as an IP version 4 at the beginning, is that clear? Any questions? The classes are defined by the range of the actual IP address. Okay. We usually use similar to your MAC addresses. The 00 range or FF are mainly booked to your broadcasting or multicasting. So there are some sort of those addresses which are reserved for multicasting and for broadcasting. So reverse addresses are, for example, 127.0.0.1 is called loopback address. So what's the loopback address? Anyone know that? What do you think about what's the loopback address? So it's like whenever you do that in your CMD, what do you have? What do you get? So in other words, you're telling you that your device is live and there's no issues within your local area network in the sense it's connected to the network and there's no problems. If there's an issue with your connection towards the network, it will give you timeout connection, that you cannot get to the internet. So you know there is an issue within your connection. So we have reserved some addresses to use it either within your local back checking, within multicasting, or within broadcasting within some sort of an address. And there are some are reserved for commercial purposes. I mentioned it in, I think, last lecture. Some companies bought large number of IP addresses just to keep them safe. And they are actually, at the moment, IP addresses not being used, just sitting there. Either 3Com mainly, that was the biggest shareholders of IP addresses, and IBM mainly. That's why we needed, they exhausted the actual IP version 4. That's why we needed a new sort of addressing. Before they went to IP version 6, we had classless inter-domain routing, which tried to divide those classes into subclasses to enable more networking and hosting addresses and subnets. And that will be part of your subnet, and that's the main part of it. There are private addresses. Look at the range of private addresses that's stored. From 10.0.0 to 255 in each of those blocks. How many of those are reserved? These are just reserved, mainly private addresses, not for a purpose of broadcasting or multicasting. Each one of those classes has a set of addresses that are being reserved by a number of companies, without mentioning who are they exactly. I don't know. IP addresses are 32-bit identifier for a host or a router interface. I just explained a router will have multiple interfaces depending on the topology and the connections. For example, looking at this topology, how many this router has as an interfaces? How many interfaces this router has? 3. Simple. Very different connections from each side of this local area network. So each of those can be considered as a subnet eventually. So the interface is a connection between a host or a router and a physical link. An actual device, the physical link connection of your PC, your Mac, is mainly by one NIC card. And that will have an identifier as a physical address called your MAC addresses. Meanwhile, your actual router will have more than one physical interface. If you try to connect through different parts of your local area network, each one of those router interfaces will be different. So therefore, there are different interfaces within your routers. Routers typically have multiple interfaces, and host typically has one interface. An IP address associated with each interface will look like something like that. So if I look at the left-hand side of the topology, you can see that the numbers are very similar. They're 223.1.1.1. Then the changes is happening in the final byte, where it's close to 2, 3, 4, depending on the number of bits. That's the subnet. Whenever I change the subnet, you can see the second byte from the right-hand side is changing, because I'm changing the subnet. So now the subnet, the actual network part, this is a class C. The network part which is changing is just the second part. And even if I create more subnets, that goes to 3, 4, 5, 6, up to 255. So I'm creating 255 subnets out of class C within this topology. So the next question is, IP address, how do I know subnets? A subnet is a part of a high bit order. If the low order are mainly the number of actual hosts, meanwhile the high order is the router itself, the subnet part of it. So if I look at the leftmost side again, number 1 is your starting point, your hosts, goes to 2, 3. Number 4 is the actual interface, the higher bit order of your subnet. Therefore, that's your interface of a router. How do I know a subnet? A device, an interface that with the same subnet part of an IP address is your same subnet, and can physically reach each other without intervening the router. So the router will jump from one subnet towards the other. So in other words, these are 3 subnets. How would I know exactly how many subnets? I detach the network. I detach the connections from all the routers. So look at the next slide here. So the recipe is to determine the subnets, detach each interface from its host or router, creating an island of isolated networks. Each isolated network is called a subnet. How many subnets do you have per heap? 3. So just what I'm doing, I'm just detaching the actual connection to the router itself. Just imagine that topology. As many as you have a connection, just detach it from the network and see how many subnets exactly do you have. Therefore, you end up with the right number of the subnets. Let's look at the slide afterwards. How many subnets do we have here?
9.
Well, detach the network. Just detach the connection to the router. How many do you have? That's 1 in the top. 2 on the, that's 1, 2, 3, what else? Those connections are 4, 5, and 6. That's it. So you detach every connection from the actual router to see your number of segments. Is that clear? Yeah.
With the routers having different IP addresses depending on the interface, does that mean they take up that many addresses?
Yeah. Any questions? So what addressing problems is still not resolved? For the moment, except that the packet has arrived towards a destination using a network address with a source IP address and destination with an IP data. We know how the packet has arrived at the destination network using hop-by-hop routing, using any type of routing algorithms. We know that the structure of a network address so can extract the host part of the address. The problem is how to deliver it to the right hosts. So, how do we know that each of the hosts of the network to deliver the packet to? What do you think? Just the MAC address. So the MAC address are needed in a sense to deliver it to the right destination. How do we know that each host has a destination added to the packet header? Again, depending on your destination addresses within the packet header, within related to the IP address and the MAC addresses. So what are the options? If I don't have an IP address, I'm just using a MAC address, this can be done by using a broadcasting procedure. So you broadcast the packet using a MAC broadcast frame. What will that create? That would create an overhead and that would create a delay. Now that's not a good option. Another option is using the both of them, i.e. you could keep a table of hosts of a network and their correspondence of MAC addresses. So what does that mean? I create a table associating each IP address within a MAC address. So therefore, every MAC address in my network will have related to as an IP address. So MAC address A belongs to the MAC address with the IP address A. If I try to reach that destination within that network or subnet, they are related, so I know exactly how they look like. And this kind of table is called Address Resolution Protocol, ARP. Okay? So we simply encapsulate the packets in a MAC frame and set the destination address to a MAC address of that host. I'll just show you we already explained the MAC address, I'm not going to do that again. I just want to show you this procedure. So let's look at this topology. Let's walk through exactly what's happening. Send a datagram from A to B via the router R. We said each router has multiple interfaces depending on the connections. In this case, how many interfaces do I have with this router? You have 2 interfaces. Each one of them has a unique MAC address. And each one of them has a unique subnet address, i.e. an IP address. So focus on addressing. At both IP datagram and MAC layer frames, you need to assume that A knows the B IP address, and you need to assume that A knows B MAC address. How's that? I'll leave that next stage. Assume that A knows the IP address of the first hop router R, and how's that again? Assume A knows the MAC address of the first hop router interface, and how? what do you use when you are in the same network and you want to know the addresses of the machine? You ask why? Using what? By broadcasting, is it? So maybe it's a broadcasting procedure of knowing exactly each one of those subnets, exactly how it's associated. So let's see how the message is being sent. So I'm trying to send a message with an IP address ones from source A towards a destination B with an IP address 2s. So clearly here I'm trying to do is using the IP address as a source as a destination. So these IP addresses don't change because I'm going to encapsulate the MAC address of that device. So I'm encapsulating the MAC source and the MAC destination. So first, I create an IP datagram with an IP source A and a destination B. And these are your IP addresses. And the second, I create a link of the frame with an R's MAC address and destination frame containing A to B IP address. So at the moment, what's your IP address source? Is ones, which is device number A. I'll do it on the board for simplicity. So I'm trying to get to the destination. So that's your topology. That's connected towards two hosts. That's A, that's C, trying to get to B, D. Each one of those devices has what? Has an IP address and has a MAC address. Okay? This interface, or this actual router, has two interfaces. Each one of those has what? An IP source and a MAC source. An IP, this side will have an IP source and a MAC source. This device will have an IP source and a MAC source. Do you agree at the moment at the principle? Each one of those devices has one IP address and one MAC address. Yes.
With the router, do both the interfaces have the same MAC or different MAC?
There are different MACs. Why is that? I just asked you a question 2 slides before. Why do you have two interfaces? You asked the question why.
I just saw the one device.
No, it is the one device, but there are two different connections. You are using it to deliver packets towards another part of the network, and you're receiving towards another part of the network. So you are connecting two different subnets, in other facts.
I just saw the IP.
No, it is this, it's different, both sides. If I'm trying to use ARP table, at the moment I'll have a table which indicates each IP address is associated to which MAC address, exactly. So if I'm sending now a packet, usually what will happen? I'll use an IP datagram. So where I have my IP source written inside here, and I'll say this is the IP destination I want to send to. In this case, what is it? Let's use an A and B. This is simple, without using the full addresses. So the IP source at the moment, what is it? I'm trying to send from A to B. So the IP source is A, whatever the number is. Okay? I'm trying to send to B. So that will be your MAC source, the IP source, sorry. We encapsulate what? A MAC address, some sort of an actual data link frame. So inside I'll have the MAC source and a MAC destination. What are the details here? Which is MAC source? What's the MAC destination? So MAC source is MAC A. So that's MAC A. What's the MAC destination then? Why? Which side has what? Why is it not the destination itself? So the question is, why am I encapsulating the packet of the MAC of this side?
Because they're two different connections. You have to find the first and transfer it.
Exactly, that's it. There are two different local area networks. There are two different subnets. You cannot get to the destination unless you reach the first hurdle before you reach the actual destination. So how many connections do I have? I have this connection first. Then what do I need to do? I need to pass on to the other interface before I go towards the destination. And from this place, I need to get to the destination. So that's it. So you do everything based on that analogy. Is that clear what happened here? Okay, I'll do it again here. Let's find out the full details. And why is that happening? So first, I have an IP address. The first step, I'm using the IP of the source and IP of the destination. The IP source is I'm trying to deliver from A to B. So use the IP address of both destinations. Then I encapsulate a MAC to reach my first part. And the first part is I'm using the MAC address of my source, which is MAC A, to reach my first interface. My first interface is router R with the first interface of E6 ending up with 4B. So at the moment the packets will be delivered towards where? Towards this interface. And the packet is now standing to be delivered towards the destination. What do you do next? Someone tell me the IP address of the source, destination, and the MAC addresses. What do you do? So what's next? Yeah, what is it exactly? So if I say what's your IP source, if I have a table, it says IP source, IP destination, MAC source, MAC destination.
Then it's going to be the MAC source.
So the IP address source, what is it at the moment? Be careful. So?
Yeah.
So the source is? So is it the same 111 or is it now the new MAC IP address of this side? So is it 111 ending with 110 or is it the same source? And why? Just what I said in the beginning, the keyword I said, I'm using the same IP datagram to encapsulate the MAC addressing. So I'm changing MACs. I'm not changing the IP addressing. Because if I change the IP address, I will lose where is the source or where is the destination. I cannot deliver that packet towards the right destination. The MAC is used to route the actual packets towards the right parts of the network. Meanwhile, those keeping those IP addresses mainly keeps the full direction of the router. So what I'm changing is, I'm keeping my IP addresses of the source and the destination. What I'm only changing is the MAC source and the MAC destination. So returning to this, the IP address source should be the same as IP8. The IP destination is still IP for B. What's the MAC source now? The MAC source of the router, of this side interface. So that would be your MAC side of the router 1. Let's call this is router 1 and this is router 2. And that will be your destination, passing all the packets to this side of the network. So looking at this, again, the packets residing on interface number 1, I'm calling it interface number 1, which is the interface with the IP address 111 ending with 110, was going to be passed to the other side of the actual router. And then, what do you do afterwards? You use the MAC address of this side of the router as a source address towards the MAC address of the destination, which is 49 ending with 2A. This will eventually reach your final parts of the destination after stripping the actual MAC layer. Is that clear? What happened here? The main part, I'm keeping the IP address, but I'm changing the MAC address to reach my right interfaces. So I stick with my IP address of the source and the destination, but I change the MAC addresses. So if I say, let's do that one, be fine?
Yeah.
Okay? So I'm trying to deliver the packets from 4523 towards my destination, 12923. Let's try it. Last year example was 16 months, I think. Something like that. Just write the MAC source, destination, IP source, IP destination, with explanation, that's all. Well, I would write in the exam, you should explain some of the things, what's happening, what you said. So I'm sending a packet with IP address source, packet address destination, details, and the MAC address source, packet address destination. So we need some details. Because I'll add to that what happened if one of those tables missing. Because we're just skipping one of the slides, I'm going to go back to it. So I want to explain this before I explain how we send a request without the ARP table. These are the subnets. Remember I said there's a subnet with a mask? So that's 24 is a mask of the actual IP address. I think explain it today. I'll explain it either in the next part of the lecture or next lecture. At the moment, the clouds are, this is referring to there are 8 numbers. Because when I say 0 and 8, that means there are a subnetting of 8. Therefore, there might be 8 devices connected. But you don't need to worry about that. You just see, because you see the range of the nodes, so you just say this is the source, this is the destination. Don't worry about the clouds. It's referring to a subnet. Yes, 45 ending up with B. So you don't need to write the full details of the MAC and the IP address. You can say that it starts with the number and end up with the B. That's fine. Okay? So the first MAC address will be 45 ending up with BB. That's it.
When you write 44 and BB.
Yeah, it's simpler than writing it full details. Okay? No, no, should be a third level.
It's not like you're rewarding yourself.
The only thing that changes
And
is
it's
how
salt.
the tricky part of this question is whenever you reach a stage where you say there's no so there's no education I make this
Mama's fun. Have a mistake. What is that? You know, 217.
whatever I need to stage you at, because it's
D3.
say how do you
The root is estimation.
I think it's 4629.
Yeah. That's source, isn't it? That's not
this idea is you don't know so they're saying
Oh, yeah.
this is very simple because it's just passive. We're not giving those things or passive. The only thing we did is the trick is when this is this, what's the IP representation? What's the passive? That's the only thing we did. Tricky. These are 1, 2, 3. That's a form. So I'm trying to create it. Each one is 1, 2, 3. If you have a connection, even if I don't know this now, so this one. Well, the tricky part would be whenever there is no IRP table associated to MAC addresses. I'll show you that later on whenever we test. This is an IRP table where you associate MAC with the source. Okay guys, let's have a 10 minutes break and then I'll do the question. I'll explain the other parts of it, okay?